right? Not electric lights, that's Edison. Electrolytes. And we had talked about electrolytes earlier in the year, we just didn't call them electrolytes. These were the things that conduct electricity, made the light bulb go on. Okay. And if you remember, conducting is charged pieces moving, so ionic compounds are always electrolytes. An ionic compound dissolves, the way it dissolves is by falling apart into its ions. Right? That's how it dissolves. Water grabs the individual ions and moves them separately. I have separate charged pieces moving. So what conducts an electrolyte is the ions that it falls apart into. So it falls apart into ions when it's dissolved. And actually, we're not going to see this, but it also falls apart into ions when it's melted. The reason why we don't show you that is because ionic compounds don't melt until they're really, really hot. Throw some salt in the pan. It's a race between what's going to melt first, the pan or the salt. Odds are neither one's going to happen on your stove. Okay, so we got the word for, we talked about ionic compounds doing this. That was the test for ionic compounds. They're electrolytes. So we have to have a name for things that aren't electrolytes. They got creative. Non-electrolytes. Substances that don't conduct electricity when melted or dissolved in water. That's a pretty lazy definition. Yeah. So they dissolve, but they don't make ions. And actually ties into, I was reading your reading guides, and ties into the most frequently missed question, which was, what two kinds of parts can you make when something dissolves? One of them was ions. But the other was whole molecules. Sugar. Put sugar in the water, the light bulb didn't go on. That's because sugar dissolved, but it didn't make ions, it made whole sugar molecules in the water. So I had pieces, but they're not charged. They dissolve because they're polar, not because they ionize. Ionize is to make ions. They dissolve because they're polar. We talked about sugar having all those H's hooked to O's so it could hydrogen bond lots of times. That's why water can dissolve a lot of it, because water's got places to hang on. Polar molecule has places to hang on to. But they don't have to make charges when they dissolve. So you have moving pieces, but they're not charged. So ionic solids don't dissolve because they have charged pieces, but they're not moving. Molecular compounds don't ever conduct because they don't make the charged pieces. I said ever, because it sounds like you either do it or you don't. But there's a middle ground called weak electrolytes. They make the light bulb glow a little bit. It's some molecular compounds. When they dissolve, they partially fall apart. A few of them will fall apart. They only make a few ions. So after it dissolves, some of them can fall apart. The most common place we see it is organic acids. I don't know if you remember last year, but you had, in biology, you studied the carboxyl group, or the acid group where it had to have that thing stuck at the end. Okay, a carbon with a double bonded oxygen and a single bonded oxygen hooked to hydrogen. That was the acid group, because this H will come off as an H plus and leave that as negative. But then we get resonance structures because this electron can go in here and make a pair, and the negative can also be up there. Because it has resonance structures, it's more stable. So organic acids are slightly ionized. Okay? That's why we use vinegar when we cook, not hydrochloric acid. Vinegar is a weak acid. A few of the pieces fall off. Hydrochloric acid is a strong acid. Everything falls apart. Okay? So the vinegar makes our food taste a little sour. Hydrochloric acid makes our teeth bubble because it's eating the calcium carbonate out. Oh. Eats our esophagus on the way down because it's got lots of H+. The H+ is the nasty part. Okay? Now, the real distinction is they don't make ions when they're melted. They have to have the water to hang on to that hydrogen. If they don't have water, that hydrogen is not coming off. Because water would be able to hang on to an H+ really easily with lone pairs sticking up there and a partial negative on the oxygen. And so, I think I found something to show you the difference between those three, if I can just find the right place where to go. Ah, there it is. It starts off with a simulation of an experiment we've seen a few times. One you did. You just did it with a smaller container. Where's my mouse at? Drag. Yeah. So, you've seen this before, right? I'm going to speed it up because they're talking and I don't want to hear them. Yeah, you put some salt in. The light bulb goes on. 3, 2, 1, yay! As the salt dissolves, the light bulb comes on. Why? Because the salt, the water hangs on to it, and it separates into individual ions. The Na plus and the Cl minus can move around, so it can conduct electricity, and all of the NaCl plus that dissolves is all falling apart. Every bit that dissolves falls apart. This is an electrolyte. Okay? Okay. Hydrofluoric acid, HF. Okay. Hydrofluoric acid, when it dissolves, come on, there's HF, stays together, except one of them falls apart. It shows about 1 out of 9 has fallen apart, so it'll conduct it's got a couple of small charges, so it'll be able to conduct a little bit. But it's really not 1 out of 10. For HF, I happen to know the number off the top of my head. It's about 1 out of every 10 million falls apart. We say few, we mean very few. Say 1 out of every 10 million, that's not very many, but remember how many there are in a mole. Still going to be quite a few, even if it's only 1 out of every 10 million. Okay. So it's a weak electrolyte. Okay, now this is methanol. It can hydrogen bond with itself, right? Because the H is positive, the O is negative. Okay, so they're trying to show you those hydrogen bonds there for methanol. Okay. Water, partial negative, partial positive. The negative part of water will be able to hook onto one side and the positive part onto the other. And that's how water dissolves something that's polar. It doesn't tear it apart, it grabs the whole thing. And since it doesn't tear it apart, it grabs the whole thing, there's no charged pieces. If there's no charged pieces, it doesn't conduct electricity. The light bulb doesn't go on. So bright light, electrolyte, strong electrolyte. Dim light, weak electrolyte. No light, non-electrolyte. Question, James? What? It's the most common one, but it's not a guarantee. Okay? Because the hydrogen bonding coming off is easy for them to do. So like I say, weak acids are the most common, but they're not the only one. Okay? So something that sort of falls apart when you dissolve it. Okay? Water. Water conducts electricity a little bit. That's why it's dangerous. It's because you conduct electricity better. Because you're full of electrolytes. Right? The water, it's about 1 in 100 million that have fallen apart. Right? And that's why it doesn't conduct electricity very well, because 1 out of a million of the water molecules has made an H plus and no H minus. So, come on, I push tab, there we go. So, strong, weak, non. Okay, water doesn't dissolve nonpolar molecules because they have no charges to attract the water molecules. Fact is, the water molecules attract each other and separate from the nonpolar molecules. Water doesn't want to hang on to nonpolar stuff. It can't hang on to nonpolar stuff. Water hangs on to water. So when you put water and oil together, it's kind of like you're out there at lunch. There are thousands of people around you, but you clump up with the ones you know. It's not because you hate all the other people, it's just you want to be with the people you're attracted to. So you form your own little clump and everybody else goes around. Well, that's what's going to happen to water. The water is going to form its own little clumps and just let the oil go around, and then those clumps of water will run into other clumps of water, and the water will separate itself from the nonpolar stuff. The reason water and oil don't mix is because water hangs on to water, not oil. So this is why oil and water separate. Okay. Now, nonpolar are just held together by dispersion forces, which is temporary partial attractions caused by the temporary partial charge in the molecule next to it. It was one of those really weak ones. That's why nonpolar things tend to have really low boiling points, is because these are weak. But they're as strong to their neighbor no matter what their neighbor is. So the reason why oil and gasoline mix is because oil hangs onto oil just as well as oil hangs onto gasoline. And gasoline hangs onto oil just as well as gasoline hangs onto gasoline. So they hang onto each other perfectly. Because they're hanging onto each other, so you pour the oil into the gas, shake it up, stick it into your string trimmer, and start your 2-stroke motor. Try to give you an idea of that. Over here, I got some test tubes. And I'm going to get some water. That's not the water I wanted. And some water. And some cyclohexane. Is it cyclohexane or just hexane? Cyclohexane. Okay. So the name ANE, A-N-E, at the end tells you it's all just single bonded carbons and hydrogens. Methane, propane, all those are just CH, no double bonds. Okay, so if I pour some water in, That's more water than I want. There's some water. And this is the cyclohexane. And I put a stopper in, and I shake them up. And it looks foamy. And then it separates into two distinct layers. Can you see the line right between the two layers? Because the water wants to hang on to the water, and the oil wants to hang on to the oil. So back here, got some leftovers from a lab. That copper 2 sulfate that we dehydrated, here it is. Okay. So if I put copper 2 sulfate into here, it's a blue crystal. I'm going to shake it up. We'll let it sit. Okay. While we're waiting for it, I'm going to make another system just like that one, where a little bit of water. A little bit of cyclohexane. Stopper on it because it evaporates really fast. Oh, notice, where's the blue in my first test tube? On the bottom. Guess what's on the bottom? Water. Copper sulfate, ionic compound. Ionic compounds dissolve in water. Okay. Here I have some iodine. I2. Not U2, I2. Iodine's a purplish solid. Now I2 has got to be nonpolar. It's got a 0 electronegativity difference, right? So when I put that in, notice where the purple appears. See how the purples all rise to the top? Because it all does the cyclohexane. Actually, down at the bottom, there's still solid I2, and that solid I2 is hanging on to the cyclohexane down there, enough to keep that drop from moving up. But as I shake it, I2 dissolves in oil. Copper 2 sulfate dissolves in water. Okay? And this is why you have to shake up your salad dressing. Because the things that taste sour and sweet dissolve in water. The things that taste savory dissolve in oil. All your herb flavors dissolve in oil. So if you want something with an herb flavor that has a little sour, a little sweet to it, you need both oil and water, and they're going to separate and then shake them up. Unless you put in something called an emulsifying agent, and the emulsifying agent will let the nonpolar hang on to the polar. Because I joke about this all the time. I say, you guys do labs and I do dishes, but I'm going to have to clean these things. Okay? And when I put them together, I'm going to clean these things. I want to go clean it. There we go. Definitely got to shake it up every time I want to use it, right? And when I shake it up, so you can actually see some, it doesn't quite, you see how it's making little drops and the little drops rise. The little drops are water hanging onto itself and pushing them out of the way. You're just in the way. I'd rather be by other water molecules. Okay. So I got to clean that. What am I going to use to clean that? Well, I'm going to use soap. This is what a soap molecule looks like in general. It's got a long carbon chain at one end, and at the other end, it's got a phosphorus with 3 oxygens. Okay? So this end of the molecule is hydrophobic, fear of water. That doesn't fear water. Water just can't hang on to that end. It's nonpolar. Okay, so it's got a hydrophobic end. At the other end, lots of charge. Water loves that end. It's hydrophilic. It's got a hydrophobic end and a hydrophilic end. A water disliking and a water loving. Water attracting. Makes sense how those two ends are different from each other. Okay. Now, I am not going to take the time to draw all those carbons, so I'm going to draw that same molecule like this. I got the nonpolar chain, and I've got the negative charge at one end. Okay. So, if I have a drop of grease in water, grease is nonpolar. Water's polar. Ever tried to rinse off a bacon pan? Pan you just cook bacon in? There's a phrase for what you're doing if you're rinsing it off. That is useless. It does nothing. The water just bounces off the oil, it goes down the drain, and nothing gets clean. I'm not wrong about that, right? Well, that's because the water can't hang on to the grease. It's got nothing to hang on to. If I want to get that grease off, what do I need? I need soap. So soap lets the grease hang on to the non-grease. Lets the water hang on to the grease. And it's because of the structure of that molecule that it can do it. Because what's going to happen to my molecule if I put it near here? I got my long chain, and I got my chain here. This piece right here wants to be in the water. This piece does not want to be in the water. Where could it be? Where could it go that it wouldn't be in the water? Well, there's one place to get out of the water. That's right there. It would like to do that. Because then the water part gets to stay in the water part, and the nonpolar stuff gets pushed into the grease, where dispersion forces can hang on to it. So that's what happens. The hydrophobic ends go into the grease, and the hydrophilic ends stay in the water. So water, the water hangs on to the soap. The soap hangs on to the grease. Because it's a molecule that can hang on to both soap and water, so it connects the two. And it's going to make the drops of grease make little balls like this. You will find that your soap water is not clear; it's a colloid. Actually, probably an emulsion, right? Okay. So water can surround and dissolve grease. You need the same thing in salad dressing that you don't want to have to shake up, like Thousand Islands or Catalina, where they stay mixed all the time for the most part. What they put in there is called lecithin. It's a protein from eggs. It's an emulsifying agent. It's got this dual personality. It's shaped a lot like a soap molecule. Yeah. Now, okay, a couple of things. First, I want to make a point here that this part of the molecule comes from fats. And this part of the molecule is a phosphate group. So, this molecule is named after the fact that it's got a phosphate group stuck to a fat. And the biology word for fat Anybody remember what the biology word for fat was? It was lipids, right? So this is a phospholipid. Okay. Now, imagine you got this thing. Oops. What the heck? That's not what I typed on. Yes. Imagine you got this, and then somebody shakes up the water, and water gets trapped in the center of this thing. That's the inside of this, becomes a bubble of water. Because that water, we want to hang on to that water, right? What would happen with the soap molecules? Well, some of them could turn around and go the other way. Put their heads in there and their tails there. Their heads in there and their tails there. Wouldn't it make sense for some of these to turn around? They could hang on just as well this way as that way. So then I would have 2 layers of phospholipids. I would have a phospholipid bilayer. Anybody remember what a phospholipid bilayer was? That was a cell membrane. That all it takes to make the structure of a cell membrane is have something polar, have something nonpolar, and have something in between. Phospholipids are naturally occurring. That this is the first stage in life because now the chemistry in the water inside can be different than the chemistry in the water outside. The first stage of life is to isolate who you are. And it happens naturally as long as you have those 3 kinds of chemicals. So building blocks of life happen just because chemicals arrange themselves so that one end stays in the water and one end stays in the fat, the grease, the lipid. Okay? So, oh no, it all ties in. Okay. So far we've talked about how solutions form and what's going to make them form. That the stuff can hang on to it. Okay? So, whether the solute and the solvent are polar, nonpolar, or ionic determines how much will dissolve effect is if it's more than 0. So we can decide whether something is going to dissolve based on whether it's polar or nonpolar. Okay. A question that is unrelated to how much dissolves is how fast it dissolves. Hey, so you want to make some Kool-Aid, and you want to make it fast. What can you do to make that sugar dissolve faster? We'll go with the obvious. What's the first one? When you stir it up, right? Everybody agree that the sugar dissolves faster if you stir it. Okay. Anybody got another one? Hot water. Hot water would work better than cold water. Here's one you probably haven't tried. Powdered sugar would dissolve faster than crystalline sugar. Think if you made it with sugar cubes. Sugar cubes would be slow, right? What if you made it with rock candy? Right? Rock candy would take a while before it dissolved. Rock candy is mostly sugar, but it takes a long time for it to dissolve. Those hard candies. And the water's hotter. We've experienced if you experience most of these, right? These are not outside your experience, so this is not a big surprise to you. That if I want to make it fast, I should use hot water, stir, and use as small particle as possible. Why? Why does stirring increase the speed it dissolves at? Why do smaller particles dissolve faster? Why does increasing the temperature make them dissolve faster? And why questions are always about what the little particles are doing. So one at a time. Stirring. In order to dissolve, the solvent molecules have to touch the solute molecules. That I cannot dissolve sugar over there with water over here. But the pieces actually have to touch each other. Because when they dissolve, the solvent molecules hold on to and surround the solute. So what does stirring do? Let's say you got your solute down here and some water is coming to pick some stuff up, right? And this water molecule picks a piece of that up and attaches to it, and it goes away. But it doesn't go away very far. All the ones that are right there at the surface, they're going to fill up right away. And you got to wait for the ones that are hanging on to stuff to get out of the way before the next person can pick it up. Everybody agree? Okay. And that's what stirring does. Stirring moves the full ones out of the way and brings unoccupied ones close by. So it dissolves faster. So the reason why stirring makes it dissolve faster is you're getting water that's not hanging on to stuff next to the stuff you want it to hang on to. It's the effect of opening up another line at the grocery store. Two people can check out at the same time. Okay. Why does particle size matter? Well, the solvent has to touch the solute. And it only touches the surface of the solute. The piece in the middle cannot dissolve until everything around it has dissolved. Unless I take that piece and cut it in half, and then the middle can dissolve right away. If I take a big piece and make it smaller, I've increased the surface area. So for the same weight, smaller particles have a bigger surface. Think about how long it would take a piece of candy to dissolve in a glass of water. It'd take a long time because you can only dissolve on the outside. And if you're not stirring, that outside gets full and everybody stops for a while until the random motion carries some new water molecules in. Okay. Bigger surface area, they touch each other more often. So smaller particles dissolve faster. Okay. Now, what about temperature? Well, what is temperature? What are we measuring? We measure temperature. Still the same answer as it was last chapter. It's kinetic energy, right? So higher temperature, faster molecules. Higher temperature makes the solvent move around faster and contact the solute harder and more often. So more pieces get broken off faster, which means it's dissolving. Temperature's different than the other two, though. The other two, all they affected was how fast it dissolves. Temperature affects how much dissolves. And it usually increases the amount of solid that can dissolve. It's not a guarantee, but it's a pretty safe bet. Changed my mind about something. Okay, so choose all that will apply. Choose all that apply. So, a solid will dissolve faster if the liquid is heated. Will that make it faster? Will it dissolve faster if you use large chunks? No. Will it dissolve faster if you stir it vigorously? What if it has a large surface area? Will it dissolve faster if it has a large surface area? Yes, that's why grinding works. Increases the surface area. More molecules on the surface, more dissolve. The mixture is put under pressure. We haven't talked about that at all. We will. And the solid is polar and the liquid is polar. Doesn't matter. Doesn't matter what they are about how fast they dissolve. What matters is what you do to make them dissolve. This will affect how much dissolves, not how fast it dissolves. And how much and how fast are different questions. Speaking of how much, there's a reason for how much. There's a reason for a limit. And the reason for that limit is simple. Remember, the solute molecules get surrounded. The solute molecules get surrounded. So eventually, you run out of solvent molecules. You got no pieces to hang on anymore. In fact, those pieces that were separated start running into each other. And if opposite charges run into each other, they tend to stick. And it starts turning back into a solid on you. That if those pieces run into each other, they're going to stick to each other. That positive and negative piece, they're going to stick to each other. And that's going to be solid. Okay, the change I was making was I wasn't happy with the homework I assigned you. We're not quite there yet. So what I'm printing out now is reading guide 13.2. I think I got enough. I'm just waiting for a faster printer. So if you want to grab one of those on the way out, and you don't have to do that, it'll be 13.2 instead. We didn't get far enough to do that, so we'll move on with that. So 13.2. Hey, that should be enough because I made 20 and that makes 40. Okay, should be enough.